So this is, you know, one of the exciting sort of first applications of, it's one of the first exciting applications of quantum computing, which sort of demonstrates evidence of a computational advantage over classical algorithms. So let me see if you can see everything here. Okay. So I really hope that, you know, you'll be able to understand this. Again, as usual, feel free to stop me with any questions you have. And because, you know, this is I guess, one of the important parts of this course. Okay. So Deutsch's algorithm was proposed in 1985 by David Deutsch, and was one of the very first to show, you know, some computational advantage, some task of quantum computers over their classical counterparts. So in this lecture, we'll understand the algorithm from a theoretical point of view. Okay, so here is the problem statement. Let me, I'm sorry, break this line. I think it looks a little ugly. What is this? Yeah, so the problem that we're trying to solve is the following. We want to determine whether a certain function f that is given to us, this is a function that maps a single bit to another single bit of output. Okay. We want to determine whether this function is constant or balanced. So by constant, what we mean is that both of the inputs, 0 and 1, yield the same output, okay? Meaning that f of 0 is equal to 0 and f of 1 is equal to 0. That's one possibility for the functions to be constant, or, you know, both of the inputs map to 1. So either both of the inputs map to 0 or both map to 1. The other alternative is that the function is balanced, meaning that one of the inputs maps to 0 and one of the inputs maps to 1. And the two possibilities for this are, you know, f of 0 equals 1, f of 1 equals 0, or the reverse. F of 0 is equal to 0 and f of 1 is equal to 1. Okay, so visually, this is what it means for the, so the top row is function f that is constant, and the bottom row shows a function f that is balanced, the two possibilities. Right, in total, there are only 4 possible functions from a single bit to a single bit, right? And the top row shows the constant functions, and the bottom row shows the balanced ones. Is the problem, or this distinction between constant and balanced, clear to you all? This is very important, so I have to make sure that it's clear to you all. Good, good. Yeah, this is the premise, so it's essential that you we're on the same page. Yeah. Yeah, that's true. I mean, does anyone not understand it? Yeah. Well, although if I ask that, sometimes people are shy. They don't want to say that they don't understand it. Okay. So now in this problem, right, you're given f and you determine whether it's constant or balanced. Now, what does it mean to be given f? Like, in what way are you given f in this problem? Obviously, you can't be given the whole description of f, because then you just look at it and look at the description and you can tell which is the case, right? The point is, in this problem, you're given f in a very particular way. So the function is given to you as a black box. What this means is that you get to query, you know, imagine there's some oracle, that some wizard that holds, you know, the function f. You get to query this oracle, on a particular input of choice to the function. And this is the only way that you can access the function. Okay, this is called black box access. You know, it's as if you have a black box on your table. All you can do is to, you know, put in an input, like the button on the machine, and then you'll get the output. But you don't actually get to see the inner working of the function. Let's put it that way. Now, of course, this is a very simple function. There's only 4 possibilities. So I guess the question, yeah, can I go back actually to the black definition? Yeah, so black box, you think of the function as you're given a black box, literally. You can't see inside, okay? And what you get to do is to input, you know, some value 0, and the black box will spit out f of 0. If you input 1, it'll spit out f of 1. Now the question I have for you is, how many queries to this black box does it take for us to be certain whether f is constant or balanced? Okay, a lot of people are saying 2, and they're saying 2 to the n. Well, here there's a single bit. So we don't have an n bit. I think I'm thinking of the n bit case. Here I'm thinking of a single bit. So 1000 says 3. Well, we don't really need 3 because, I mean, only 2 possible inputs. So there are only 2 things that we can query. It's at most 2. But in fact, you know, we need at least 2, exactly 2. You know, if we were to query the function once, you know, for example, query on 0, we get back f 0, and then we have no information whatsoever about the value at 1. Right? So, you know, once we get f of 0, the function would still be constant or balanced. You know, until we get information about f of 1, we will never know whether it's constant or balanced. So we need exactly 2 queries. And so the purpose of Deutsch's algorithm is, okay, good, there's a type, good. The purpose of Deutsch's algorithm is to do better than this, right? So since the classical solution needs 2 queries, we want quantum equivalent of this problem that can solve it in just a single query. Okay, which seems quite ambitious as a task. I mean, how is that even possible with a single query? There is a but essentially what Deutsch's algorithm gives us is an algorithm that does this in a single query, which is quite remarkable. So I'll tell you what the caveat is. So first, let me sort of review one piece of mathematical, you can say, notation that we need for the rest of this lecture. So this will be a 2-part lecture, by the way. So I think the first part will go on for 40 minutes or so, and then second part will also be 40 minutes. So the first thing I want to sort of briefly review is the parity. So parity of a sum. So we use the symbol, you know, this symbol here. Let me answer a question first. I don't get why do we have to do the query step. So yeah. So the problem is the following. So you're given a black box access to f, and the problem is, you know, how many queries does it take you to determine with certainty whether f is constant or balanced? So you only have access through the to f as a black box. That's the statement of the problem. Okay. And classically, you need 2 queries to determine with certainty whether f is constant or balanced. We will show that quantumly a single query to f is sufficient. So this is, you know, this is the the setup of the problem. We want to determine in this model where you can sort of query f only as a black box, how many queries does it take you? Yes. Thanks, Andrew. Good. Yeah, so the query is the number of times you run f of, yeah, exactly. Yeah, so, okay, so back to this parity symbol. Yeah, this is called also XOR, if you're familiar with that. But basically what it gives you is just the parity of the sum. Okay. Some people, it's a sum modulo 2, if that means something to anyone. So basically, you know, I'll call this symbol XOR, that's how I usually call it. So A XOR B is equal to 0 if A plus B is even. In other words, if A plus B is either 0 or is equal to 2. Okay. And A plus B is equal to 1 if A plus B is odd. And here A and B are just bits, so they're either 0 or 1. Okay. Does the definition of this XOR symbol make sense? Mm-hmm. Great. So, okay, let's just get a little bit practice with this. I hope you can still read what it says here. So what is 0? Oh, you can't read, cannot read it. Okay. Oh, how do we do this? Actually not sure how to make it bigger. This doesn't make it bigger. What is 0 plus 1? Sorry, 0 XOR 1. Any guesses? Yeah, 1, it's odd. Okay, I just have to check that I'm making sense. Good. That's the correct answer. Now, okay, I mean, 1 plus 1. Okay, I think you guys get it. This is 0. And what is 2 XOR 3? Yeah, so here if I'm taking A and B to be any integers, yep, so it's odd. Good. So you all are getting it right. Very good. Now, okay, now this is slightly more complicated. Does, yeah, is it true that, yeah, so the answer should say true or false, yes or no, but does A plus B plus C, when I say plus, I'll say, you know, XOR or plus interchangeably. When I say plus, I really mean this symbol, okay? So what does A plus B plus C, sorry, does A plus B plus C equal A plus B plus C? Yeah, so some people are saying no, some people are saying yes. So does it matter the order if we have a sort of a XOR or sum of 3 things, does you know, the order in which we sum them matter? No, it doesn't matter. So the answer is that they're equal. So the answer is that they're equal. The order does not matter. So these two quantities are the same. And yeah, I mean, with the, so how to say it? Yeah, so I guess the easiest way to see it is that, you know, if you were summing the 3, you know, A, B, and C, in a normal way. So without doing this parity business, even or odd, you're just summing the three things. Of course, you know that that this sort of order in which you sum the things doesn't matter, right? If I'm just summing the numbers without worrying about the parity. So the quantity on the left would give me the same as the quantity on the right. The same number, okay, say 17, okay. And then after that, you're taking the parity of 17, which has to be the same for both sides. This is, yeah, this is exactly the associative property. So associative property holds also when you're doing this XOR business. Okay. Yeah, if you're not convinced, you can check it for yourself and do some verifications, but it should be fairly straightforward. Now, okay, suppose that A and B are bits, and suppose that they're equal. What is A XOR B? Okay, good. Very good. One last thing. No, okay, obviously if they're different, okay, you get one. That's fine. Okay, I thought there was one more exercise, maybe not. Okay, good. So I think you all get it. That's very good. So let's move on. I don't know why it always renders like this. Okay. Yeah, in a nutshell, yeah, what Fauzan says is absolutely correct. Just ask, are the bits different? True. It's one. Are they? If they're, yeah, if it's false, it's 0. How did I get it to render properly? I just ran it again. I just ran it again. Okay, so querying a function quantumly. So when we talked about the classical version of the problem, we were saying, you know, you have this black box on your table, you can input some value and it will give you, you know, f of that value. And I told you, you know, we'll have an algorithm quantumly that only takes a single query, but we'll have to make a caveat on what does it mean to query this, this function, okay? So the caveat is that we will have sort of quantum access to the function in some sense. Let me be a bit more precise about what I mean. So one way that you could think of how to model sort of access in the quantum case is to say that, you know, you're allowed to input to this black box a qubit in the state, say, you know, 0. And what you get in return is f of 0. That's one possibility, but, you know, you get them as quantum states, right? So, for instance, in the quantum case, the black box could be performing the following. So it's a unitary that when you input cat 0, it returns f of 0. And when you input cat 1, it returns f of 1. Okay, and remember that to specify a unitary evolution, all we need to do is to specify, you know, how this unitary, this gate, acts on the standard basis. So on cat 0 and cat 1. Yeah, unitary was something that, so a unitary is, you remember, is this condition that we imposed on a matrix that describes a quantum gate, or a linear transformation that specifies a quantum gate. And unitary means that it preserves the, you know, the norm of the vector that we multiply with the gate. So I guess what I want to say is, remember that quantum gates map vectors that have norm 1, to vectors that have norm 1. And the unitary matrices are precisely those matrices that map vectors with norm 1 to vectors with norm 1. And these are, exactly, unitary matrices or unitary linear transformations are exactly the same set as set of quantum gates, valid sort of quantum transformations. No normalization required, exactly. It's baked into the unitarity. Okay. So when we want to sort of formalize quantum access to a function f, since sort of evolution of quantum states happens, either by unitary or by a measurement, but let's restrict ourselves to a unitary for the moment. We have to specify a unitary implemented by this black box that is sitting on our table. Preserving the norm, what I mean is that if the vector had norm 10, after multiplying by matrix, it still has norm 10. If it had norm 1, it still had norm 1. Okay, now one thing to notice is that if the matrix is such that it maps any vector of norm 1 to some other vector of norm 1, okay, it will also be the case necessarily that it maps any vector of norm 17 to vectors of norm 17. This is something that you can convince yourself about. Norm equals amplitude. No, so norm was the magnitude of the vector. So if the vector is like AB, yeah, so it's the modulus of A squared plus the modulus of B squared. This is the norm squared. So you take the square root of that. It's the magnitude, how long the vector is. Okay, so to specify black box access to this function f in the quantum world, we have to specify a unitary or some quantum gate, right, implemented by this black box that is sitting on our table. The simplest, so the first idea that we can have is that the unitary is going to act on the standard basis in this way. So 0 maps to f of 0, 1 maps to f of 1. Okay, noted about the unitary. We will improve that. So now is this sort of mapping that I've written here, so cat 0 mapping to f of 0, cat 1 mapping to f of 1, is this a valid quantum gate? Is this a valid, if you were to write it as a matrix, would this be a valid transformation or not? Would this be a valid quantum gate? That's the question that I'm asking you. So this is a single qubit quantum gate. It's specified by 2 by 2 unitary matrix. Would this be in general a valid quantum gate? Yeah, f only goes to 0 and 1. Yeah, so people think that this is a valid quantum gate. So we haven't really okay, well, in a way, yeah, we have given you the tools to detect that it's not, but we haven't really sort of emphasized that part. So Khurshid is correct. Imagine that this function f was actually constant. So both f of 0 and f of 1 are equal to 0. Okay. Then in this case, the transformation that this quantum gate is implementing is it's mapping cat 0 to cat 0 and cat 1 to cat 0. Okay. Now, as Khurshid pointed out, this is not a unitary. In particular, one of the conditions for being, one of the conditions for being sort of a unitary was that there exists, if you sort of multiply u by this matrix U dagger, which is the obtained by taking the transpose and the complex conjugate of U, then you get the identity. What this means is that you can reverse U. So U has to be invertible. So any quantum gate, and don't worry if this was not clear to you. This is not something that we really emphasized in the course previously. But a consequence of being a matrix that preserves the norm, or that maps vectors with norm 1 to vectors with norm 1, a consequence of that is that you have to be reversible. Okay, so there has to be another unitary, okay, that undoes the effect of the original unitary. So does that make sense? You can ask me actually, like what doesn't make sense or what I can clarify, because this is not a point that that I stressed. So yeah, so actually I was saying, you know, one sort of the first naive natural way to define this unitary is, you know, on the standard basis, it acts in the following: it maps 0 to f of 0 and 1 to f of 1. Now, we don't know whether f is constant or balanced yet, right? But if f was constant, then what I claim is that this mapping doesn't define a valid quantum gate. Like mapping, if f was constant, then, you know, both of the right-hand sides are 0. Say, you know, they're both equal to 0, for example. In that case, cat 0 maps to cat 0. Cat 1 also maps to cat 0. And this does not define a valid unitary. So one way to see it is that it actually does not preserve the norm of vectors. For example, let me write it here. So I don't have the iPad on me, but for example, if you consider this state here, okay, and you imagine that this unitary, this black box maps 0 to 0 and 1 to 0, okay, then this state here would be mapped to, you know, 1 over square root of 2, 0 plus 0. Oops, what did I do? Right? This is equal to 2, you know, 2 root of 2. Yeah, exactly. So if it were balanced, it would be a unitary. But if it's constant, what happens is the following, right? So this vector 1 over square root of 2, 0 plus 1, which has norm 1, would be mapped to the following: 1 over square root of 2, 0 plus 0, right? So far, so good. And this is equal to 2 over square root of 2, 0. Now, the norm of this last vector here is not 1. The norm is exactly 2 over square root of 2. Okay, so the norm, the vector which initially had norm 1 is mapped to a vector that does not have norm 1 anymore. So this, if the function f was constant, this mapping that we define here would not be unitary. It does not map vectors of norm 1 to vectors of norm 1. Does this example make sense as to why, if f was constant, this mapping here would not define a unitary? You should care about unitary functions because sort of one of the axioms of quantum mechanics is that sort of evolution, so the evolution of quantum states is in two ways, either measurements or linear transformations that are unitary, that preserve the norm. So these are the only two things that are allowed. So if I don't write a unitary function, this is not a valid quantum evolution. It's just not something that happens in the real world. So anything that happens in the real world has to be a unitary evolution. That's why we care about unitary functions. Okay, so anyway, I think we've spent enough time sort of arguing why this sort of the black box implementing f cannot be just simply doing this mapping here of 0 to f of 0, 1 to f of 1. The way that we make this sort of mapping unitary is the following way. Yeah, so this is a valid, so okay, just before I move on, to summarize, one important fact to remember about the discussion we've just had is that, if you forget about anything, about unitarity or anything like that, the one thing that is really important to remember is any valid quantum gate has to be reversible. It has to be, it should be possible to undo the gate. So to apply a gate that maps back to whatever original state you had. And clearly, if your function maps, all of the inputs to 0, it's not possible to reverse this. So the workaround that we have to define black box access to the function is the following. So instead of just saying, the unitary defining f maps single bits in qubits, okay, we will say that this black box maps, x, y to x, y plus f of x, okay. So in other words, if I input x on the first qubit and 0 on the second qubit, what I get in return is x, x, okay. If I input x in the first qubit and 1 on the second qubit, what I get in return is x and the XOR of 1 with f of x. Okay. And it's possible to check that this linear transformation defined in this way, it's actually unitary. So it's a valid quantum state. In particular, the way that we resolved the fact that the previous function was not reversible is that here, we're keeping track of the input to the function x, whereas before we were throwing it away. We were just saying 0 maps to 0, 1 maps to, 0 maps to f of 0, 1 maps to f of 1. We were completely sort of throwing away the input and just keeping the output. And here we're still recording what the input was. We're not throwing it away. So it's always possible to reverse this transformation, given, okay, the way to see it is, given x and y plus f of x, I can always go back and recover x and y. Whereas before, if I was given, in the case that the function f was constant, if I'm giving an output 0, I don't know if it comes from a 0 or from a 1. Whereas here, because I'm keeping track of the input, I can always undo this. Is there anything that I can clarify on this? I realize that maybe this is a little bit hard to digest.
Andrea, this is Lorraine. So let me see if I got this.
Yeah.
We're saying that the wave function x tensor product with wave function y maps to x tensor product with y exclusive or the function of x?
Yes.
Okay. And why do we say that?
So we say that because the way that we did it before, okay, what we had, the mapping that we had before was not a unitary mapping. It was not reversible. If I map sort of if I only use a single qubit, right, and I map, 0 to just f of 0, 1 to f of 1, okay, this mapping is not going to be, it's not reversible. Should I clarify what I mean by reversible?
Well, if you have an output, it means that you can figure out what the input was.
Exactly. So in the case that I'm mapping, 0 to f of 0 and 1 to f of 1, okay, if the function f is constant,
then you cannot map it back to the input.
I cannot map it back, right? Because in some sense, I've lost all the information about the input once I go forward. Like, I don't know whether the output came from a 0 or it came from a 1.
Right, but if it's balanced, you can map it back.
If it's balanced, yeah, but we want, we want some sort of solution that works for, both constant
both
and
cases,
balanced.
okay.
Yeah. Now, in this case, yeah, go ahead, sorry.
I was going to say, so with this equation, what you're saying is, hey, if we know what x is and we're given the output, whatever, the y or the function, we can figure out what the input was.
Exactly.
In either case.
Exactly. Now, if I'm given x and y plus f of x, I think qBraid was asking, how do we recover y? Okay. Now, say that you're given something in the form of the right-hand side. Okay. So you're given x and then y XOR f of x. Okay. You can use x to compute f of x, right? And then you just sort of subtract f of x from the second part. So you'd have y plus f of x, but you subtract f of x from the second part. And this gives you y again. Okay, sorry. Unfortunately, I don't have my right here. Let me try to write it. Bear with me for a moment. So if I'm given this, I can always sort of take, I can always compute y. So I can always compute this quantity, right? If I have x and I have y plus f of x, right? I can always use the first sort of qubit of the first bit x to compute f of x, okay? And then sort of sum it or subtract it, it's the same for the XOR for the parity, sum it to the second bit, right? And if I do this, I would have started with f of x. I sum an additional f of x, and this gets me back to y. And so in this way, gone from the right-hand side back to the left-hand side. I've recovered y. This, okay, qBraid says that he got. Well, okay, that's a good question. So Emily is asking, what does Y represent? So Y doesn't represent anything in particular. We have to, so ideally, you know, what we would define is just simply this mapping here. So x of x0 goes to x f of x. We don't really care about Y. But in order to make it, make this mapping sort of unitary, we have to define how this this unitary acts on all of the possible states of 2 qubits, and that includes, you know, I possibly being also in not only 0 state, but also in the 1 state. When we define a mapping on 2 qubits, we have to define it on all the possible sort of standard basis states, and that includes Y, which could possibly be 1. Although what we really care about is when Y is equal to 0, because then, you know, x0 maps to x f of x. So basically what would otherwise be a 1 qubit thing, we need to answer Jagger, we need to stretch it to 2 qubits to make it invertible, okay? With Y as the second qubit. Yeah, we have it there because that's the only, we have to define how you're acting on the second qubit, basically. What we really care about is when Y is equal to 0, essentially. And Lauren, is this clearer?
Thank you.
Oh, okay, good. Okay. Okay, very good. Yeah, so now, you know, we no longer have the problems when we use 2 qubits. We no longer have the problem that 2 inputs are mapped to the same output, which made our, our mapping not reversible. Oh gosh. Anyways, we will show that, you know, a quantum computer that has access to this unitary mapping here at the top, which we'll call U with a subscript F, okay, a unitary implementing F in the sense of the first line above here. We will show that a quantum computer with access to U sub F can determine with certainty with a single query whether the function is balanced, whether F is balanced or not. So you're still allowed to query it once, use, you know, this unitary gate once in your circuit, and that will be enough for you to determine with certainty whether F is balanced or not. Okay, and one remark that has been cut out just before we proceed is that, you know, remember that the problem of determining, or notice if you haven't noticed it, the problem of whether to determine whether F is constant or balanced is exactly equivalent to determining whether F of 0 XOR F of 1 is equal to 0, or whether it's equal to 1. Right? Whether the two are the same, in which case it's 0, or whether F of 0 and F of 1 are different, in which case it's 1. So really, all that we want to determine in order to solve the problem is the value of F0 XOR F of 1. This is exactly what we want to determine. And we will do this with a single query to this unitary U sub F. Oh gosh. Okay, so then you might be slightly worried that this new sort of black boxes, unitary black boxes we defined, you know, with this extra XOR operation, might be sort of more powerful than the original sort of classical black box that we had, right, in the classical case. Is anyone worried about that? You know, that now, you know, we've kind of changed the problem a bit too much in a way that this quantum black box is too powerful. Loren, yes, good. Okay, good. I'm glad I can address that. So, well, one thing that might make you feel better is that, you know, you can Yeah, it seems that we have changed the problem, and I'm absolutely with you that we have changed the problem a little bit. In fact, you know, this is not a. That's why this algorithm is one of the first proposed, you know, in 1985. It gives evidence that quantum computers can do better than classical algorithms. It's not like a proof, because we have slightly changed the problem. But one thing that can make you feel a bit better is that if you gave a classical algorithm, you know, access to the following black box here. Okay, so XY, you know, you can input to this black box XY, and what you get in return is X, and then Y XOR f of X. Okay, let's say, you know, we gave, you know, even in the classical case, we gave you access to this, you know, seemingly more powerful black box. Okay, then you would still, you know, what you can argue is you would still need 2 queries to this black box, even to this black box with the XOR operation. You still need 2 queries to determine with certainty whether f is constant or balanced. And the reason is as simple as each classical query, you know, even with this more complicated black box, it still gives you only information about either f of 0 or about f of 1, but not about both. And you need information about both to determine whether f is constant or balanced.
Yeah.
Yeah.
Couldn't you, because I'm looking at that saying, well, that should be easily to implement. You have X and Y going into your black box.
Yeah.
On input, you're reading X, and you're taking the input Y, and you're doing an exclusive OR with the output.
Yeah.
And wouldn't that give you the answer then?
The answer to
Whether it's balanced or not?
what's your proposed algorithm?
Okay, so you take the output, and which is f of x, and you do an exclusive OR with y from the input. Wouldn't that take it there?
No, because, okay, let's say you input, you know, let's say x is equal to 0.
Okay.
Right? So you input 0 y, let's say.
Okay.
Okay. You would get 0 in the first
Bit.
Input, yeah, in the first bit, which doesn't tell you anything. In the second bit, you get y XOR f of 0.
XOR f of 0. F of 0. Okay, yeah.
Right. So there's no information whatsoever about f of 1.
Oh, okay. All right.
Right.
Yeah.
Like y is completely, you know, independent of f of 1. Like it has no.
Yes.
Yeah.
Okay.
So, you know, if your x is 0, you will only ever get information about f of 0. If x is 1, you only ever get information about f of 1.
Okay.
Yeah.
So I'm sorry, I guess advanced, but so then how are we getting that information with the quantum computer?
Yeah, I will get to this in a moment. So hopefully this at least, you know, makes you a little bit more, you know, feel a bit better that, you know, this black box that we're giving in the quantum case is, you know, not so much more powerful, right? I mean, even if we gave this, you know, what I wrote here, you know, in the classical case, you still would need 2 queries. Whereas, you know, quantumly, we'll see we only need 1. So it is still a little bit more powerful. Like, you're right that we're still changing with the problem, because in the quantum case, you're getting access to a unitary, like a quantum gate, implementing this function. Whereas in the classical case, it's just some classical mapping. So we are changing the problem, because in the quantum case, you're getting access to like a quantum gate. So you, in particular, okay, what the key will be is that you can put, for example, the first bit or qubit x, you know, in superposition. Okay, so you can put the first bit x, instead of having it, you know, either 0 or 1, you can put it as a 0 plus 1. Okay, and then on the other side, you would get a superposition of things that depend on f of 0 and f of 1. So you are kind of getting information about both f of 0 and f of 1 at the same time, even though they're in superposition. That's how that's one thing that we will exploit, basically. But hopefully this becomes a bit clearer in the second part. Yeah, so this is an exercise that you can do later, just to familiarize yourself with U sub f. Okay, but not clear yet. Yeah, so hopefully the quantum part will become clear later. I hope at least the classical part, Laren, is at least clear. Okay, so let me take a break here since I've gone already for almost an hour, and then we will resume for the second part. Okay.